For the longest time, the story in AI has been pretty simple, right? Bigger is better. More data, more parameters, more raw power. But what if a brand new breakthrough just completely flips that script on its head? Okay, let's dive into this tiny model that is seriously challenging the giants of the AI world.
All right, so to really get what's going on here, let's start with a few puzzles. I mean, these are things that seem pretty straightforward for us humans, even if they might take us a minute to figure out.
Okay, first up, you've probably seen this a million times. A classic 9 by 9 Sudoku. It's just a game of logic, isn't it?
All right, how about this one? A pretty complex 30 by 30 maze. The goal is simple. Find the shortest path from the start to the finish. Again, this is something you or I could totally solve with a little bit of trial and error.
And finally, let's look at an abstract IQ test. This one comes from a benchmark called ARC. So here's how it works. You get shown these before and after examples to figure out a hidden rule, and then you got to apply that exact same rule to solve the main puzzle.
Okay, so here's the kicker. What if I told you that some of the world's most powerful AIs, the ones with trillions of parameters, get a score of 0% on some of these? I mean, they completely and utterly fail. That's the mystery we're going to unpack. Why do these massive models struggle so much, and what in the world is the new approach that actually cracks the code?
So to really understand this new solution, we've got to get to the root of the problem first. And it all comes down to the fundamental way today's huge AI models are built to think.
And this leads us to a pretty big paradox at the heart of what we call deep learning. You see, models like the transformers that power things like GPT are incredible at language, right? But here's the thing. Their reasoning depth is actually fixed. And computationally speaking, it's pretty shallow. They have a set number of thinking layers, and that's all they get. For a simple question, no problem. But for a really complex, multi-step puzzle, they can't just decide to think deeper. They're stuck.
So the workaround we've been using for this is a pretty clever trick called chain of thought, or COT for short. You've probably seen it. It's where you tell the AI to think step by step. You're basically forcing it to write out its whole reasoning process, breaking down a big problem into a bunch of smaller language-based steps.
But listen, the researchers behind this new model we're looking at today, they don't mince words. They call chain of thought a crush. Think about that. It's just a patch, a band-aid, not a real solution to the fundamental problem of shallow thinking.
And here's exactly why it's just a crutch. First off, chain of thought is super data hungry. It's also completely dependent on language. I mean, think about solving that maze. Do you literally talk yourself through every single turn? Probably not. And on top of that, it's brittle. One tiny mistake in that long chain of text, and the entire solution can just completely fall apart. The bottom line is, it's just not how we humans actually reason.
Okay, so if the current approach is basically a dead end, where do we look for inspiration? Well, the answer is pretty obvious when you think about it. The most efficient and powerful reasoning machine on the planet, the human brain. See, our brains don't have some fixed number of thinking layers like those AI models. Instead, neuroscientists have figured out that we operate on these really cool principles. We use a hierarchy. You've got high-level parts for the big picture strategy and low-level parts that handle the nitty-gritty details. And these systems work at different speeds. That fast and slow thinking idea. Plus, we use these constant feedback loops to refine our thoughts over and over. This right here, this is the blueprint for a better way.
So, how do you take these incredible brain-inspired principles and build them into a new AI architecture? Well, say hello to the Hierarchical Reasoning Model, or HRM for short.
HRM is built from the ground up on that brain-inspired blueprint. So instead of one giant flat network, it has two distinct modules that work as a team. You've got the high-level planner. This one is slow, deliberate. It sets the big picture strategy. Seriously, think of it like the boss. Then you've got the low-level doer. This module is lightning fast, crunching all the detailed calculations based on the boss's plan. It's the subordinate who's actually executing everything. And this setup creates this amazing dynamic reasoning loop. Here's how it works. The planner sets a goal. The doer then runs tons and tons of super fast computation cycles trying to hit that goal. The results get sent back up to the planner, who then refines the strategy, and the whole cycle just repeats. This is how the model achieves what's called computational depth. It gets there by iterating and refining, not by having some massive, rigid architecture. It can literally think for as long as it needs to solve the problem.
Okay, so the whole brain-inspired design sounds amazing in theory, but does it actually, work? Let's get to the results, because honestly, they are absolutely astonishing.
First things first, let's talk about size.
The HRM model that used for these tests has only 27 million parameters. Let me say that again, 27 million. In today's AI landscape, that's practically microscopic.
Just to put that in perspective for you, a massive model like GPT-4 is estimated to have over 1 trillion parameters. That means HRM is over 40,000 times smaller. It's not just a little car, it's a go-kart racing against a freight train, and it's about to win.
So how does this tiny engine actually perform? Well, on that abstract IQ test, the ARC benchmark, HRM scores an impressive 40.3%. That's way better than much larger models like Claude. And get this, it does this with only about 1,000 training examples and with no pre-training on the entire internet. It's unbelievably efficient.
But the Sudoku results. This is where the story goes from impressive to just plain jaw-dropping. You know those huge models that rely on chain of thought? They scored a perfect 0. Zilch. Couldn't solve a single puzzle. Meanwhile, HRM, our tiny little model, solved 55% of them.
And it just keeps getting better. On those really hard 30 by 30 mazes, it's the exact same story. The giant models, 0% accuracy. And HRM, it found the perfect path almost 75% of the time. Look, this isn't just a small improvement. This is a monumental leap forward in how we think about AI reasoning and efficiency.
So what does all of this mean for the future of AI? Are we looking at just a clever niche trick, or is this a truly fundamental shift in the game?
Okay, let's be real here for a second. The strengths of RHM are crystal clear. It's incredibly efficient, it doesn't need a ton of data, and it pulls off this deep, iterative reasoning that feels a lot more like how we think. But it's not a silver bullet, at least not yet. It's proven itself on these kinds of logic puzzles, but the next big challenge is generalizing this approach to the messy, complicated worlds of human language and computer vision.
And that leaves us with the huge question that's really at the heart of this research. For years, the main path forward has been brute force scaling. Just build it bigger. But HSRM points to a totally different path. A path where the key to smarter AI isn't just about scaling up, but about building smarter from the inside out, using hierarchy, inspired by the elegant and efficient design of our own brains. And if that's the true path forward, well, that could change absolutely everything.